So, given a vector, say suppose you have a vector x1, x2, x3, okay, and this is in 3-dimensional space, 3-dimensional, they say Cartesian space, for example. I mean, so you can expand this vector in this basis x2 okay. So, I mean this vector is a vector in R3, and you can see here, I mean I expanded, I mean say for example I call 1 0 0 as ket 1 and 2 as 0 1 0 and 3 is 0 0 1. And you can expand in this basis in 1 2 3 and ket 1, ket 2, ket 3, that basis, any arbitrary vector in this space can be expanded in this basis, okay. And this basis, these are basically the natural basis in R3, okay, in R3. And some similarly, I mean okay. So, now suppose you have a matrix ABCD, and you can expand this 2 cross 2 matrix in this basis A into 1 0 0 1 plus B into 0 1 0 0, sorry, this is 0 plus C into 0 0 1 0 plus D into 0 0 0. Okay, so this is a I mean here you can see that these four matrices forms the basis for the natural forms the natural basis, forms the natural basis. Okay, so I mean so the space of this 2-dimensional 2 cross 2 matrices, I mean it's actually it's a 4-dimensional vector space, right. So you need 4 bases, I mean 1 2 3 4 bases to represent a 2 cross 2 matrix. Similarly, suppose you have a 3 cross 3 matrix, so you will have 9, so say for example this is like A11, A12, A21, A22. If it is a 3 cross 3 matrix, then say A11, A12, A13, A21, A22, A23, A31, A32, A33, and then you can expand this as A11 into 1 0 0 0 0 0 0 plus etc. up to A33 0 0 0 0 0 0 0 0 1. Okay, you can expand it like this. So, I mean the corresponding vector space, it is a 9-dimensional vector space. Okay. So, okay, so if you have an n cross n matrix, then it will be n square, that will be the I mean that will be the dimensionality. All right. Now, if you take for example, I mean so if you take a matrix, say 2 cross 2 matrix for example, say A, B, C, D. I mean I told you the choice of basis, I mean it need not be the natural basis, you can have any other basis. I mean so I choose a particular basis where I take this as m into I2 plus or I0, m0 I0 plus or sigma 0, m0 sigma 0 plus m1 sigma 1 plus m2 sigma 2 plus m3 sigma 3, and this sigma 0, sigma 1, sigma 2, sigma 3 forms a basis, forms the basis, okay, where sigma 0 is the identity matrix 0 1 and this is sigma 0 is equal to I2. and sigma 1 is 0 1 1 0, and sigma 2 is 0 minus I 0, and sigma 3 is 1 0 0 minus 1. And these three matrices, they are known as the poly matrices. Poly matrices. Okay. So, these are the coefficients M0, M1, M2, M3 are the coefficients. Let us find them out, and then we will talk about the properties of the sigma matrices. Okay. All right. So, I can write this as M0 ABCD, which is equal to M0 into, so you can say that M0 into identity, M0 0 0 M0 plus M1 into sigma 1 is 0 1 1 0. So, it will be M1, we have M1 M1 plus M2 into 0 minus I, so minus I M2 0 plus M3 0 0 minus M3. Okay, or this is equal to, you will have M0 plus M3, and you will have M0 minus M3 here, and then you have M1 minus IM2, and here you have M1 plus IM2, and that should be equal to ABCD, the matrix ABCD, which tells you that, that means you have A is equal to M0 plus M3, and then D is equal to M0 minus M3, okay, which implies that A plus D by 2. So, M0 is equal to A plus D by 2, and M3 is if you subtract this, so M3 is 2 M3 A minus D by 2, okay. And the next equation is B is equal to M1 minus IM2, and C is equal to M1 plus IM2, okay. So, B plus C, or M1 is equal to B plus C by 2, and M2 is equal to C minus B divided by 2I, which implies that I into B minus C divided by 2. Okay. So, these are the expanded coefficients. M0 is A plus D by 2, M3 is equal to A minus D by 2, and M1 is equal to B plus C by 2, and M2 is I into B minus C by 2. These are the expansion coefficients. All right. Now, so these are the bases, right. So, and now you look at a 2 cross 2 matrix whose trace is 0. If the matrix whose trace is 0, then you can expand usually with this, but you look at what is M0. M0 is A plus D by 2. What is A plus D? A plus D is basically the trace of the matrix. So, if you are expanding the traceless matrices, then you do not need this, because M0 is already 0. So, there the dimensionality will be 3. Okay. So, you can say that a traceless 2 cross 2 matrix can be expanded in terms of just the poly matrices, you do not need the identity to expand that. So, so the dimensionality is 3. So, you will have sigma 1, sigma 2, sigma 3 as the basis vectors. Okay. All right. So, now again you take okay. So, given a matrix like this, so I told you you can expand. I will just write A11, A12, A21, A22 as A11 1 0 0 1 0 0 plus A12 0 1 0 0 plus A13 sorry A21 0 0 0 1 1 0 sorry 1 0 plus A22 0 0 0 1. Okay. And here I mean you can write this as I mean so what the basis in R2, the basis in R2 is going to be equal to I mean R2 is 1 0 and 0 1. This is 1 and this is 2. This is ket 1 and ket 2 is 0 1. And R3 it will be 1 0 0, 2 will be 0 1 0 and 3 will be 0 0 1. Okay. Similarly, R4 I mean you can construct like that. I mean so I am just using R2 and then I will generalize to this thing. So what is 1 1? So 1 1 is equal to you will have 1 0 1 0. So that is equal to 1 0 0 0. And what is 1 1 2? 1 2 is 1 0 and then 0 1, that is equal to 0 1 0 0. Similarly, you can write 2 1. 2 1 is 0 1 1 0, that is equal to 0 0 1 0. Similarly, 2 2 is equal to 0 1 0 1 and that is going to be equal to 1 0 0 0 0 1. Or you can expand this matrix like the following. I mean so you can write this as A11 1 1 plus A12 1 2 plus A21 2 1 plus A22 2 2. Or and this is the case of a 2D matrix, but for example in for a 3 cross 3 matrix you can in the basis you can write 3 cross 3 matrix A11 A13 A31 A33. Okay. This can be I mean so you can generalize it as summation over ij equal to 1 to 2 I comma j, which is equal to 1 to 2. You can write Aij ij as a matrix. I equal to I comma j equal to 1 to 2. So if the 3 cross 3 matrix, it will be I comma j equal to 1 to 3 Aij I comma j, and in this way you can expand the matrix. Okay. All right, and suppose that now okay, so if you have a matrix, okay, and you can find the eigen, you know how to find the eigenvalues of the matrix. So if you have a matrix A 2 cross, suppose A which is a 2 cross 2 matrix, okay, you can find the eigenvalues of this matrix and then you can find the eigenvectors also, and then take the normalized eigenvectors, and using the normalized eigenvectors you will be able to so I mean the eigenvectors will be like this: A acting on some ui which is equal to lambda I ui. Okay. So I mean so the lambda I is the eigenvalue corresponding to the eigenvector ui. Okay. So this ui ui are the normalized ui, the normalized eigenvectors. These are the normalized eigenvectors, and using this these eigenvectors act like a basis. It's also a basis, right? This is also a basis, and this basis is known as the eigenbasis of that matrix. If A, this is the matrix A. So, what I am saying is these are the I mean once you can find the orthonormal eigenvectors, and this orthonormal eigenvectors forms a basis, and this basis is known as the eigenbasis of the matrix A. Okay. And now you can expand, I mean, so the question is the following, and you know how to compute, right? Given a matrix A, you will be able, you can compute the eigenvalues and eigenvectors, and then you can find the eigenvalues or the eigenspectrum, eigenvectors. And now I say that I will give you the eigenvalues and the corresponding eigenvectors. So, will you be able to construct the matrix? Okay. Okay, you can do that. So, in order to do that, so you write A, you already know ui is equal to lambda I ui. Okay. So, you then multiply with ui. So, A ui and then ui, you multiply with corresponding bra vector, and then it will be lambda I ui ui, and then you sum it over I. Okay. So, you know that A into this will be some A into summation over ui ui. Okay. So, from I mean you know that from because it is an orthonormal basis, because of from the completeness you will get A is equal, this is identity, summation over I ui will be identity, and then you can write A is equal to summation over I lambda I ui ui. Okay. And this is known as the spectral expansion of the matrix. Okay. So, I mean in terms of the eigenvectors of the matrix, you can expand. So, once you know the eigenvalues and eigenvectors, these are the eigenvalues corresponding to the eigenvector ui. So, once you know the eigenvalues and eigenvectors, you will be able to compute the matrix. I will give you examples when in the tutorial session. We will do explicit examples for this. Okay. So, all right. In this class, we will just look at functions of matrices, and we will just start with the exponential of a matrix. All right. So, suppose M, sorry, A is an n cross n matrix, is an n cross n matrix. So, what is e power A? The exponential of a matrix. So, generally, I mean, if you know, I mean, you have, suppose x is a variable, and e power x, if x is a number, then you can say that 1 plus x square by 2 factorial, this is expansion of e power x, right, plus etc. etc. Okay. So, that will be the case. Now, in the case of exponential of a matrix, similarly you can define it. So, you have I, this is an n cross n matrix, I n cross n plus A plus A into A divided by 2 factorial plus A divided by 3 factorial plus etc. etc. Okay. So, as an infinite series, you can define this is the exponential of a matrix A, e power A. And here this is an n cross n matrix. So, A is already an n cross n matrix. So, this A square also will be an n cross n matrix. So, basically e power A is going to be another, it's an n cross n matrix. Okay. All right. So, let us just try to evaluate the exponential of a matrix okay. So, and then we will generalize it. So, we will take a particular matrix and then we will generalize, I mean do a general formula for that. Okay. So, suppose that your I need to find e raised to I sigma 2 theta, okay, where sigma 2 is the Pauli matrix 0 minus I 0. Okay. In the last class we discussed about and so you can see that, I mean, what is sigma 2 square? Okay, in the assignment in the tutorial session we will describe the properties of the Pauli matrices. So then we will okay. So what is sigma 2 square is again, so it will be I2, it will be identity. You can see that you take the product of sigma 2 into sigma 2, you will see that it is going to be identity matrix. Okay. So e raised to I sigma 2, where theta is some parameter, and you have I sigma 2 theta. Okay. So e raised to I sigma 2 theta by definition, which is equal to identity plus I sigma 2 theta plus I sigma 2 theta whole square divided by 2 factorial plus I sigma 2 theta whole cube by 3 factorial plus I sigma 2 theta raised to 5 divided by 4 divided by 4 factorial plus etc. etc. Okay. All right. So this is equal to I plus I sigma 2 theta, and I square is minus, right, minus sigma 2 square is identity. So minus theta square divided by 2 factorial, okay, into identity plus here you have I cube will be minus I. So minus I sigma 2 cube will be sigma 2, because sigma 2 square is identity. So sigma 2 cube will be sigma 2 divided by 3 factorial sigma 2 into theta cube divided by 3 factorial plus I raised to 4 will be 1 and sigma 2 raised to 4 will be identity. So theta raised to 4 divided by 4 factorial into identity plus etc. 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 All right. So this is equal to, and now we will have two types of this thing, the terms which will have identity matrix, and then we will have terms which will have sigma 2. Okay. So I can write identity into 1 is a minus the second type theta square divided by 2 factorial, and then you have theta raised to 4 divided by 4 factorial minus plus I sigma 2 into theta, then minus theta cube divided by 3 factorial plus etc. etc. Okay. So e raised to I sigma 2 theta, which is going to be equal to, what is this thing? This is cos theta. So I2 basically, I2 cos theta plus I sigma 2 and I sigma 2, and this is going to be sin theta. Okay. All right. So this is what? This will be cos theta 0 0 plus I into 0 minus I 0. So I square it will be equal to 1. Minus I square will be 1 and this will be minus 1, so into sin theta will be sin theta minus sin theta. Okay. Or this is equal to cos theta minus sin theta minus sin theta cos theta, or basically this is r theta, the rotation, right, in the xy plane. So this is the cos theta, this is a rotation matrix basically, right. So e raised to I sigma 2 theta is nothing but this. Okay. So you can see that, I mean, it's an exponential of a matrix, and see how it's again, as we said, it's a 2 cross 2 matrix, and it's a very familiar matrix for you. Okay. Now given an arbitrary, I mean, similarly you can generalize it to I sigma dot n theta. Okay. So we will discuss this in the tutorial session. Okay. So, okay, fine. Now given, suppose that you have a matrix and suppose that you have a matrix A, okay, and let this matrix be a diagonalizable matrix. That means A is a normal matrix. If A commutes with A dagger, that is if A is equal to A dagger is equal to 0, then you say that it's a normal matrix, and normal matrices are diagonalizable in principle, and this can be diagonalized by a similarity transformation. That means you can say lambda, which is equal to S inverse AS. By doing a similarity transformation, you will be able to get a diagonal matrix. Okay. So this is okay. So all right. So now you need to. So if lambda is equal to S inverse AS, then what is A? A is if you multiply S from the left hand side, so you will get S lambda, and if you multiply from S here, S into S inverse will be identity, and then S lambda S inverse. This will be your A. If A is lambda is S inverse AS, then A will be equal to S lambda S inverse. Okay. And now I need to evaluate e raised to A. Okay. So to evaluate e raised to A, I know what this is identity plus A square divided by 2 factorial, or A into A divided by 2 factorial, plus A cube A into A divided by 3 factorial, plus etc. etc. Okay. So instead of A, I can substitute for S lambda S inverse, where okay, this lambda is a diagonal matrix. You know what is when you diagonalize the matrix, you will get lambda 1, lambda 2, lambda 3. The eigenvalues at the as the diagonal elements, and all other elements will be 0. That is what you get when you diagonalize a matrix, you will get it like this. Okay. So this is equal to identity plus A instead of A, I can write S lambda S inverse plus this A S lambda S inverse into S lambda S inverse divided by 2 factorial plus S lambda S inverse S lambda S inverse S lambda S inverse divided by 3 factorial plus etc. Okay. And similarly, I can write identity as e raised to A, identity as S inverse. Okay. S inverse. So instead of I can write S inverse. So I will take S from the left hand side, S out from the left hand side. So you will get an S inverse from the right. So what will you get? So you will have 1 or identity there, identity plus lambda plus here you can see that this will become identity. So S into lambda square S inverse. So you will have a lambda plus lambda square. In the next term, this will be identity and this will be identity. So lambda cube by 3 factorial plus etc. etc. Or this is equal to S into e raised to lambda S inverse. Okay. And this will be e power A. Now, what now you look at what is e power lambda, what is lambda? Lambda is a diagonal matrix. Say for example lambda 1, for example let us just take the case of a 2 cross 2 matrix. So lambda 2, you have 2 eigenvalues, that will be lambda 1 and lambda 2 here. If it is a 3 cross 3 matrix, you will have lambda 1 0 0 0, lambda 2 0 0 0, lambda 3, that will be the case. Okay. So if you want to write e raised to lambda, okay, so you will have identity plus lambda, lambda is this matrix, lambda 1 0 0 lambda 2, okay, plus lambda square. So this square is going to be equal to 1 by 2 factorial into lambda square, right. So, this is going to be, if you take a diagonal matrix, this diagonal matrix and square it, you will get lambda 1 square 0 0 lambda 2 square, plus if you cube 1 by 3 factorial lambda cube, this lambda cube will be, you will get lambda 1 cube 0 0 lambda 2 cube, plus etc. So, e raised to e raised to lambda, you get it as identity plus okay. So, identity is what, 1 0 0 1, right, plus this quantity. So, you will get 1 plus lambda 1 plus lambda 1 square divided by 2 factorial plus etc. 0 0 1 plus lambda 2 plus lambda 2 square by 2 factorial plus etc. And what do you get from here? You will get e raised to lambda is nothing but e raised to lambda 1 0 0 e raised to lambda 2. Okay. So, if you take a diagonal matrix and exponentiate it, so it will be the just exponential of the diagonal elements. E raised to lambda is equal to e raised to lambda. If it is a 3 cross 3 matrix, you will have diagonal e raised to lambda 1, e raised to lambda 2, e raised to lambda 3, all other elements will be 0. Okay. All right. So, to calculate e raised to a, you can easily, if you know the eigenvectors, you will be able to easily construct e raised to lambda. Once you know lambda from the eigenvectors, you will be able to construct the matrix S. So, once you know the eigenvalues and eigenvectors, you can easily compute eigenvalues and eigenvectors of the matrix A. You can easily compute the exponential of the matrix A, exponential of the matrix like this, S into e raised to lambda S inverse. S is a matrix which consists of the eigenvectors. I mean, you know how to diagonalize what is the S matrix and all, like from your degree classes. Okay. So, now let us evaluate determinant of exponential of A. Okay. And determinant of exponential of A is going to be equal to the determinant of S into e raised to lambda S inverse. Okay. So, this is equal to, I mean, you know, determinant of the product of matrices will be determinant of S into determinant of e raised to lambda into determinant of okay. So, I mean, you do not need to do that, you can just try to, I mean, sorry, you can write this as determinant of determinant of S into determinant of e raised to lambda into determinant of S inverse, and determinant of S into determinant of S inverse is going to be identity. So, it will be determinant of exponential of lambda, and you know already you know that e raised to lambda is e raised to lambda 1 into e raised to lambda 2, e raised to lambda 3, etc. So, determinant of e raised to lambda will be determinant of e raised to lambda will be e raised to lambda 1 into e raised to lambda 2 into e raised to lambda, etc. So, it will be e raised to lambda 1 plus lambda 2 plus etc. So, the sum of the eigenvalues is actually equal to the trace of the matrix. So, you can write this is equal to determinant of the exponential of trace of A. So, this is the determinant of exponential of A. So, I can write determinant of exponential of A, which is equal to exponential of trace of A, exponential of trace of A. Okay. Here I again determinant of exponential of lambda is going to be equal to e raised to trace of A, because the sum of the eigenvalues is equal to the trace of the matrix. Okay. So, again I will do a few examples of 1 or 2 examples in the tutorial session for this one. All right. And similarly, I mean, you can define the log of a matrix, the cos of a matrix, the sine of a matrix, etc. Okay. So, that we will do in the next class.